I could put a photo of me nada among days, not to have a woman. She is also important.
Yeah, you are correct.
I will suggest that. She is the proper name to put to, with Komogoro fly. There must cannot be another one. I have a suggestion. That you managed to put a photo of any Nader here. I There's a place here. No, I have a suggestion. Please, yeah. You manage a photo of any Nader. Mona manager? Any Nader? Yeah. Nader? Here, because to have any Nader?
Any other, yeah.
Yeah.
Oh,
Maybe,
yeah, of course.
Yeah, maybe because that's the only name I can think.
No,
that,
of course. That's a very
that
good
can,
suggestion. Definitely.
that can
Yeah.
be in this company.
No, actually, these posters are not generally available. One of our colleagues went abroad.
Yeah, I
and
can
he
imagine.
got these
This
very
is
nice
good.
posters.
Yeah,
from
this is
Kapu.
very nice. Yeah.
Kapu that he could collect at that time. That was the pre-internet days.
Yeah.
Those posters he got.
This one is
and
very good. I have
gifted
never
those
seen.
posters to this.
I have
department.
never seen this photo before. That one, okay,
The other file, the MP4, is that open somewhere so that it's minimized, like.
Yeah. Why doesn't to, because it is, no, I don't understand. Why doesn't want to go back? Okay.
Is it being broadcast now? Or it was, huh? Live. We're expecting a few more colleagues. Okay, let's wait for a few minutes. Class.
এই বোর্ডের এই জায়গাটা উনি করছিল তখন থেকে। যদি কেউ বোর্ড খেলতে চায় তখন
পেলাম না রোহিত ফোন
Welcome everyone to the second Ashok Maitra Memorial Lecture by Professor Maria Maria Eulalia Vares.
Thank you. Thank you very much for the opportunity and the invitation. So there is an overlap between this talk and the second part of my talk in Bangalore. So I hope this is not a nuisance, but maybe some people will be bored if they attended the other one. So it's based on a joint work with Tom Mumford, EPFL, and Hal Schuer, who was his student when we did this work. And the reason I chose it because it combines percolation and SPDs. So I think this combination that it's not always around. So, and I'm thinking that I'm not talking for experts in either of the topics, so I kind of give a few general words about motivation, about percolation, which is very close to mathematicians, not only because of the coffee. So the mathematical modeling started with Simon Broadbent and John Hammersley back in 57, thinking of putting a mathematical structure to understand large networks. And it is interesting to know, though, that a bit before, there was this very interesting experimental work by Rosalind Franklin. And if you go to see these papers, which are can be found here through the internet, you see that it contains a lot of data, a lot of quantitative analysis. Not, of course, it was not a mathematical work. So, and she was interested in density and porosity of coal. I mean, the interest for percolation in the beginning exactly was very much connected with the mine. And Broadbent and Hammersley themselves were thinking it as a way to model masks for
So was this Rosalind Franklin the same
the
person?
same,
of
the same, the
SDNA?
same. Yeah, she is more famous
Yeah.
because
The
Yeah.
Rosalind.
yeah. So there are two basic examples. One of them they somehow appeared in a mixed way in this talk. So the one that Robert and Hammersley introduced was the Bernoulli percolation on ZD. So you might think that you have your Z, D, Z2, let us say, for each bond, each pair of nearest neighbor, you toss a coin. This coin has a probability P of being head. And then if it's head, you open the bond. If it is otherwise, you don't open. So you get a random graph. So that's the Bernoulli percolation, just the Bernoulli measure on the bonds. The other one, which appears also in somehow in this talk, is in our work is the Erdos-Renier, very classical example, the Erdos-Renier random graph. So you have n vertices, and you connect each pair with probability p independently. So you get a random graph. This is very classical graph. So let me say something about this example first, because it will, I hope, make a step towards our model somehow more clear. So the model is this one, which I already said. You have two parameters, n, which is the number of vertices, and p, which is the probability to keep the edge. So you have your complete graph, and you start erasing edges. So you keep the edge with probability p, you erase with probability 1 minus. So one thing which is which is interesting, that this model has also the Bernoulli, but I'm focusing on this because it has to do with what we are doing today, has a phase transition. This is very classical. When you take P 1 over n. So if you take P lambda over n, then there is a phase transition when it passes through 1. And how is it manifest? This is already done by Erdos and Reni. So if lambda is bigger than 1, then there is a very big component, a so-called giant component, which is of order n. All the others are small because it occupies a big part of the space. And if lambda is less than 1, then all components are very small. And lambda equal to 1, that's the critical case, let us say, the largest component is of order n to third. And already Erdos-Reni had proved that the two largest components are of this size. This was significantly refined in the work of Aldous and Martin Leff, more or less at the same time, independent works. They are written in a different, a little bit different, but the main ingredient is this one. So instead of just looking at lambda equal to 1, you look at P equal 1 over n, you look at a window around 1 over n. That this allows a much better understanding. So if you take P in this window, 1 over n plus u 1 over n for third, okay? Then you see that the clusters behave as n2, they have their order is n2 third, but they have an asymptotic distribution. This is proven in the paper of Aldous. And I'm not so sure how it's everything follows if I were looking only Martin left, but in Aldous paper, this is very clear. So if you take in some way you look at these components, say order the biggest, the smaller here. If you, I mean, some of them could be 0, and then everything, the rest is 0. And then this converges in law in some suitable space. In this sense, is L2, space of C, but in distribution. And this explains how, what is the asymptotic distribution of these as n goes to infinity. This divided by n over 2 goes to a relevant variable in distribution, and the distribution is given as the excursion of a reflecting Brownian motion, which has a drift which depends on the time. So the drift at time s is u minus s. This is not important for what I'm going to do. I just mentioned because it's such a beautiful thing. So there appears the multiplicative coefficient. What I'm going to do has basically to do with p equal 1 over n. The simpler setup. But anyway, so of course, this is the components of percolation. You can think that this is the same in this Erdős-Rényi if you were looking the so-called mean field SIR model for epidemics, also called Reed-Frost epidemic model. So what is that? Say you have a population which is fixed, is n individuals. There is no spatial structure. That's Erdős-Rényi. Each individual can be in 3 states: susceptible, infected, or recovered. So it's an infection that once you are cured, you are immune. Okay, so and let us think of it in the simplest setup. That means discrete time, because that's construction of percolation. It can be like that. So each infected individual can infect one of the susceptible ones with probability p at random. There is no spatial structure at all. It's like in Erdős-Rényi graph. So if there are 10 infected, 10 susceptible ones, for each of them there is probability, the same probability. And then this period of the infection is simply 1. That we are looking at just a discrete time evolution. And after that, it is immune. This individual is immune. So of course, this is a dynamical way, if you think a little bit, a dynamical way to construct the graph of the various components. If we start with two infected individuals, you are going to construct the components of this in the percolation of these individuals in the Erdős-Rényi graph. Okay, so the critical value, as it's known, is 1 over n. So the lambda critical is 1 over n. This is what everybody became so familiar with the language, of epidemiology due to the COVID pandemic. So that means R0 that people speak in epidemiology is close to 1. It's the same. So this is just another way to look at this model. So what happens is that if the number of infected individuals is much smaller than the susceptible ones, this grows like a branching process because the chance to get to try to infect someone who had already been removed, had already been infected, is small. So it behaves like a Galton-Watson process, critical Galton-Watson. And let us now see what this allows to say in terms of dynamics. So suppose you start at time zero with n to the alpha infected individuals with a constant in front, like let's say order n to the alpha. And you look at the evolution of the number of infected that you have at time n alpha t, you divide by n to the alpha, and you look the total number of R is all those that have already been infected. That's the removed one. All the population. So this is everybody which you already constructed in the clusters, no? Because that's R. R is simply form the clusters of those initially infected individuals. So you know that one can prove that this converts to a process in distribution as n goes to infinity. I'm looking only at p equal a half, equal 1 over n, so it's simpler. But you can look at more refined, a window around. But I'm just looking at this because it will help me to talk about the model I want to talk. So what is known is that if your alpha is less than 1/3, then the y behaves as if it were just branching. It converts, the y is a diffusion, the Feller diffusion. So the same as for a branching, critical branching process. On the other hand, if alpha is 1/3, then you have this attrition because try to infect someone that is already infected, and this doesn't count because it is already immune. So you have to subtract this drift, which here is y, and here is the integral from 0 up to t of y. So there is this attrition. So this fits, it's essentially the same with the way that when he said that the final size of the epidemic is of order n to the 2 alpha. That means it is another way to speak about the maximum, the components of your graph. And in fact, this has been written in a more precise way. It follows, for this model, it follows from the work of Aldous and Nightingale, and also for a window around the critical. But then there will be a drift term also here. But since I don't need that for what I'm putting this because it will allow to see more clearly our model. So there is this attrition that involves y and the integral from 0 to t of y, because whenever you try to infect someone that was already infected since time 0, this doesn't count because you look in this way, or you look that you are constructing a component of percolation, and then this is already included. So the fact that there are 2 ways or 3 to reach doesn't matter. Okay? And it's important to comment just for, they also look at the, here in, though this name is difficult to say, and Lale also looked at the SIS model. That means after being infected, after a time, say unit time, or depends on, you can put an extra parameter, the individual is susceptible again. This would correspond to a percolation oriented when you add the time. So it's a different model and different scaling. The scale is not 1/3, but it has the same behavior. So the one thing which I want to keep is this one, though the parameters will be different than in my model, but there is this attrition which is natural, and this follows from the same kind of argument. So now let me go to the model that I want to talk about. And this is a percolation model, edge percolation on Z2, which has in one direction, say horizontal layers. It is like very close to, though the graph is different, you have, so here each vertex has two n neighbors on that line, and he can connect to each of them with 1/2n. So it's like a critical, if it were just considering the same analogy what we have, just that the graph is different, is Z. So on the other hand, there are also nearest neighbor vertical edges. So they are just size 1 vertical. And these vertical edges, they are open with a small probability that for the moment I don't say exactly what it is. Okay, so it is, you can think that you make the same sort of construction, dynamical construction, thinking of infection model if you wish or something. So each one on the, if I look restrict only to a line, so it branches with the average is 1, the Bernoulli binomial 2n 1/2n, and then puts a child at the place where this succeeded. No, so there is a usual branching and walk. Okay, so this first has a number and position, and then you put the children in this place. This first generation of the children. Then you might go again, no? The children, the grandchild, but maybe this one was already constructed because that is as in the Reed-Frost epidemic model. So this was already removed, so it was already infected, or as you say, and then it doesn't count. So and you keep doing this. So, but you might, since it is critical, there is a, when it's small, it behaves as the critical as the branching. After a while, it will feel that is not branching. There is this attrition. Just that your graph is different. Your graph is infinite, but you are doing this from edge any place. Okay, so on the horizontal line, I have this. On the other hand, of course, if you are restricted to a line, it will never have an infinite component because it's finite range. N is a parameter fixed. But there is also this vertical thing. Sometimes you go to the other city and you start spreading the infection in the other city because there nobody knew the virus, so everybody is susceptible, and you can create this other cluster here, and so on and so on. And you ask yourself, the question that you ask is if there is an infinite cluster or not. That's what you ask. Since I am on the plane, then it makes sense to ask, is that a positive probability? Starting, say, from one individual or for 200 individuals, does it infected? Does it have a probability that this remains forever? So let me just show some simulation. It's not any important simulation. It's just to give an idea of how it looks like, no, just to illustrate, let us say. To have a picture of this. So it spreads more in this horizontal and so it has this kind of. So that one failed quite often, it finished. This one will be more successful. Then you have this spread out in this direction and nearest neighbor in the other. Okay, it's vertical can go up and then can go down again. And you see here it went down. It's not oriented. Okay. Okay, that's enough because here it's not important. So this is the model that I want to say something about. And we want to know if there is a critical value of B. Let me recall what is B. B is this. The probability to have a vertical edge to be open is 1/n to the B. And there is a kappa in front, but the important thing is the B. Why? So what I want to know, is it true that I can find a B such that when everything else is fixed, I see a phase transition as I vary this constant in front of this n to the minus B. B is critical in this sense. There are two universal constants, C1 and C2, that don't depend on n, such that if kappa is less than C1, there is no percolation. If kappa is bigger than C2, there is percolation. I mean, to wish that C1 is equal to C2 is too much, so I don't put that. Okay. Not only in the theorem, but not even in my wishes. Okay, so that's so to exhibit percolation means to have an infinite open component, which is the same to say if I start with one, I look at the component of one side, it's positive probability to be infinite. You might ask, why are you interested in this type of thing? Well, because it looks a bit strange. But the motivation comes from a question in statistical mechanics model, which is the so-called easing with Katz potential that I mentioned yesterday, Katz potential. So, and it's, I will maybe say a little bit about what is the difference, but this one, that's where we got. So, because it's common, you see these probabilities are very different. Here it's very spread out, and in this direction it's near the neighbor. So when you look in interactions of, say, in even in physics, say in nanomaterials, you might have really be interested in very thin layers which interact only vertically in a very short distance, and in another direction they interact more spread out. So that's the kind of thing. But our interest was mathematical. But anyway, there are some, because all these things which are real, they are indeed connected with quantum thing, and we are doing something. So in order to answer this question, the main point is to understand, forget the vertical edge, is to understand very well what is the component of a vertex in one line without activating any of these bonds, vertical bonds. Because once you know this very well, maybe you can do some scaling, because this is a kind of continuum approximation that is spread out. So if you scale, you see something continue, and you might hope to, let's say, but to understand this is very important. So, and if you think that, I need to understand this, you are immediately left to think of this Erdos-Renyi, this SI. Just that here it's infinite. So, but there is something that reminds you, because 1/n is critical. At each one has branch like it's a branch in random walk, tries to make a branch in random walk with critical. So by the time you don't see much attrition, this behaves like a Galton-Watson critical, and not Galton-Watson, because there is a position, a space, no? So there is branching random walk critical. So you expect it to behave in a manner that is well known. And then you need to figure out which is the good scale at which this behaves differently, like in the result that I mentioned before for the finite set. Here it's infinite, but you need to behave that. So what I'm saying here is I look at the component of the origin restricted to the line. There is nothing else. My problem is only on the line. Okay? I look at. Yeah, sure.
You explain once for how the connectivity probabilities depend on the local information, the horizontal and vertical capabilities.
Yeah, this will be there. I'm taking always 1/2n on the horizontal.
Horizontal and
Yeah, always this one critical. Yeah, it's interesting to know if I would take a window around this in the same way as others. We didn't do that. Take a near 1/2n. We took only the exactly critical one. So you can construct this guy similarly as the Reed-Frost model, no? Or you take as it was in the picture, I start from the origin, I see the children, that's the first generation. Then I see the children from the children, each one goes to his house, but sometimes the guy comes to the same house, so it doesn't count because you are constructing a set. So these are generations, and then I'm calling C hat K the process. With K means just that it was obtained after time K. Okay, so this is C hat K is going to have value 0 or 1. It is in the connected to the origin or it's not. There is a path that brings there or not. That's only that. Okay, but it's naturally to think as the same way as we were when we were talking about recalling this Reed-Frost model, that to compare this with the branching envelope. The branching envelope is that, well, just the branching random walk. There are a certain number of children, the children go to their houses, and then the children from the children might come back to the house of the parents, no problem. You get a lot of people in the same site. This is the branching random walk. You could have that. Okay, that's why I call branching random walk envelope, in the sense that it's naturally that you couple this, that this guy is less or equal than that, but the other one could be 100 and the other is going to be 0 or 1. Okay, because if it comes a second, it doesn't count. There is a twist. Okay, so at each time, this branching random walk is simply this. The occupied sites branch according to the binomial with average 1, 2n, 1/2n, and each one moves to the 2n neighbors uniformly. That's the branching random walk. Okay? And we want to know what happens with this process in the limit as n goes to infinity. So for the branching random walk, it is clear. Though we write the theorem, but this is well known essentially, that the scaling limit is the Dawson-Watanabe diffusion, the same analogous to what in the case where no spatial structure, it was the Federer diffusion. So there is a diffusion process that describes what happens with the envelope. And in order to figure out which is the right scale, to know which is the size of my true process, I need to catch the proper scale where the attrition matters, which in the other model was 1/3, n to the 1/3. Here it's another one, it's another graph. but we need to find out which one, and then understand if there is a scaling limit of the true process. Now, since all this is getting like that, it's naturally that the way we have to treat this is to make a continuum limit and to look at as make a rescaling and to see the process in the limit as a function. Okay, so there is a related work which somehow also helped us to go through it, inspired us a lot, this part, which is by Lally, Steve Lally. And what he's doing, he's not doing a question in the plane, he's looking at what he calls discrete time spatial SIR epidemics. So what is that? He has a sequence of torus. So each of these has n individuals. These are villages. There are all these villages on a line of villages. Each individual can infect anyone in its own village or in the two neighboring villages. And with the same probability. So it's critical also. So Pnij is 1 over 3n because there are n guys here and here and here. So each one can, that's the critical. So it's corresponding to our case, just that the graph is different. But it is quite similar. You expect to have a close behavior. So that's what Raleigh does. And he finds out the scaling limit for his process. And unfortunately, we cannot use his result, not only because the graph is different, but also the techniques of his paper, since he has a discrete time process, he managed to do it by looking at the log likelihood from with the attrition, without the attrition, and we cannot do it because ours is not that. So, but instead of following this route, we follow a somehow more classical, maybe, which has also been used by other people, and I will mention as I get to the theorem. So we want to see what happens to detect which is the scale at which my process the attrition which separates makes different the behavior of C, the envelope, the branch envelope, than C hat, which is the true process. Okay? I need to detect that. Okay, so so in order to make a continuum limit, we need to scale down space. So we make all this 1 become 1 over n, so that the range becomes -1 to 1, just since we want to make a continuum limit. And so we make the horizontal edges, scale them so that they become between -1. So the 0 goes up to 1 over n, 2 over n, up to 1, and -1 over n, and so on, up to -1. These are the things. And I'm going, so this is the same system, I'm just looking at with the smaller scale down. And now I'm going to apply this to this system that I'm interested in. I'm applying a diffusive limit. So I just change the scales, n alpha for space and n2 alpha for time. It's a diffusive limit because since we expect that for the branching walk we should have a diffusion in the limit, then natural to take a diffusion limit, diffusion scale. So we take these two, space and time, and in this way your process goes from z, this n to the 1 plus alpha, into 0, 1. That's just have changed the scale. So the neighbors, two guys are neighbors if in this distance they are less than n minus alpha, because this corresponds to what I had before. That's trivial. And the right way to look at an approximate density, because I want to see that there is a limit in the continuum, is to take how many in the neighborhood, so how many y's in the neighborhood of x, and divided this by n to the alpha with a 2 because it's symmetric. So it is maybe not totally obvious that it should be in this way, but a little bit of computation makes it clear. And we want to know what happens with this guy. That's why you figure out that alpha, this should be alpha because it has the right behavior. We want to know what happens to this guy when n goes to infinity for each given alpha. Okay, so since our main point is if there is percolation or not, you are allowed to start with any number of individuals in the beginning, any finite number. So we just start with something which approximates the function 1. So we started with, we put on this guy, because this is our, which corresponds to minus 1, 1, we put particles equally spaced. So the interdistance will be this. So I have n to the 2 alpha 2 because everything is symmetric here. Go one side and another side. You have these 2n, 2 alpha particles, integer part because I don't want to bother, equally spaced on this. So it's an approximation of minus indicator of minus 1, 1. In this scale, it's the right approximation. Okay? So we start with this, just to, because my main goal is to know if there is percolation in the plane. So I don't mind starting with. And we want to know what happens as n goes to infinity. Okay, so let us first, following the scheme which we planned, let us first look at the envelope. The envelope is the branching with the branching random walk. So it's a very simple process. What you constructed the envelope at time n plus 1 at x, meaning you look at all the neighbors of x, sum of all the neighbors, you see if there was a child born there that wanted to go to x. So this is just Bernoulli's independent. And so this sum here is what gives you C. And how many you have depends on how many are at y. Now, so this is a trivial construction of the branching random walk here. So, and okay, the density is defined in the same way for this process. And the first theorem, which is probably, it would be almost unnecessary to write it down as in the proof, but it's better to be safe and right, is that no matter what is alpha that you have chosen, this will convert for the envelope, it will converge in law to the Dawson-Watanabe diffusion. So this is a diffusion, this is a diffusion process that is well defined. And to know, I mean, the proof you need, we cannot use the same argument as I said already, that kind of tool that Lale uses for his convergence because of different setup. But so we follow kind of more classical way. You want to prove that converges to this can be described as the unique measure which satisfies a given martingale problem. So you prove tightness and you prove uniqueness of the solution. So that's what we do. And in order to, I'm not going to do details, but in order to understand why it should be that equation, you simply write down again the formula which describes how you obtain Cn plus 1 from C of n. You just add and subtract this guy here, and you see that it is this one here, which is added, subtracted here and added here. And you see that you get here this a term which will give a space-time white noise because these atoms are Bernoulli independent with probability success probability 1/2n, and here you get a Laplace. So it's a matter of making it vigorously. So you need to prove tightness, and then there is unique solution of that martingale problem. So this part is very similar to some way that Carl Miller and Roger Tribe dealt with. They were looking at different process. I think was the Volter model, not this one, but it's similar. So you prove that this converges. The convergence is in the usual way, weak convergence of the probability measures on the space of square Hart trajectories, where they take values is a suitable subspace of the continuous function. You want basically continuous function that don't grow too much. Now you need to go to what matters to us, which is when does it come the attrition? We need to figure out which is the alpha where I will see a different behavior between one and the other, because these scales for the moment they are whatever they are, the same way as in the SIR model. Okay, so one first thing is that whenever we want to start to understand the attrition, we need first to know when there is multiple occupants with very small probability. At most one particle at the site with very large probability. And we need to see that. So we just examine that and examine also the total mass. So total mass is in this case for this process is simple to compute. It's just what we had before for the okay, but now we need to understand is when I have more than one particle per site with a small probability. For envelope, the envelope process can have, but when this probability is small. And then you compute without too much trouble, and you see that this is okay, provided alpha is less than 1. That number is going to go to 0. So, okay, alpha less than 1, but it's not enough. No? So now we need to go to the true problem, which is to look at the true horizontal process and figure out at which alpha I will see things different than which alpha, and then what is going to be the behavior of this process. So the true process takes values just 0 and 1, and I can construct in a similar way as we had before, which is to vary from step k to step k plus 1. This k is the time, k plus 1. I need to know that someone wanted to go there. That means this one, which is similar to what I had before, that some children want to go there, and that this place had not been occupied before, because if it was already occupied, there is no point. So there is this condition which involves the sum since time 0. Okay, and you have that. Okay, manipulating a little bit with this, you figure out that this guy can be written as this part here, which is from what is the Bernoullis at this time, and this one, which is 1 minus the process since time, the integral. Let's say this is the integral in time since time 0, plus some error. And this error, this is truly an error, and this involves proving that if alpha is less or equal than 1/3. So for the moment you say, so if I want to compute this better, I take alpha less or equal than 1/3, because then I have an expression which I already can manage a little bit more. And with some more effort, that maybe I don't know if I if you want the details, because what I want to say is that I need to manipulate a little bit this expression, because in order to see that the attrition, to write this in terms of my xi, and to see that which is the right alpha. So maybe before I do that, and I do if you prefer that I do, I state the result. So what you can prove is that if alpha is 1/5, then it's the right scaling at which you see a convergence of for the true process. The density of the true process will converge in law to something which was, as before, and there is this term. So if you believe what was there in the Erdos, in the Reed-Frost model, which you have to subtract y times the integral from 0 to t of ys ds, so you probably believe this. You think that I'm not cheating, and we can prove it because it's somehow very similar, no? That's why you have to subtract this is because whenever it goes to a place which had been already occupied, it doesn't count. So it's in the attrition. But it is easy to guess why it should be that. Because, and I kind of make a sort of hand-waving argument why it should be that, why it should be 1/2. Because you can think the following: you couple the two processes, C hat and C, in a certain way. You start with the same, and then whenever, say, let us call red part, just to use the same language of Lawler, no, I wrote wrong here, Lale. So this is wrong. Lale, if a particle goes to a place which is, if a particle, say, I call particles which are blue or red, and the blue are the red are, say, the good ones, and the blue don't count for hat, only for C. So if, which one I said? I said the blue don't count. Okay, so if any child of a blue one is blue already by definition. And if a red particle has a child and this goes to a place which has been occupied, it's blue again. It's like killed. And then you need to see how much this attrition comes in, no? So you couple them. So at each time, you started with 2 N2 alpha particles. And at most 1 per site, they were distributed in this number of, this is my initial configuration. So if you divide this by that, you know that you have N to the alpha minus 1 particles per site, no? Because 2 alpha and this N 1 plus alpha. That's how I started, my initial configuration. Well, branching in random walk is critical, so it will remain the same until it dies for all the time. And the time that will die is of this order, because that's how many guys you start for the branching random walk. Okay, so there is, during all this N to the 2 alpha, now this attrition comes because you sites cannot be visited again. So there is that for each particle, the attrition is N to 2 alpha and alpha times N alpha minus 1, because that's particles per site. Whenever it goes to a place where there is a particle, it's like killed. So this is per particle is N3 alpha minus 1. But now per generation, since it's N2 alpha, is N2 alpha times N3 alpha, because each generation has N2 alpha particles. So it becomes N5 alpha minus 1. So to be critical, alpha should be 1/5. That's a kind of hand-waving argument, and then you prove. But it is then there is a better in order to prove. Okay, so the proof of this is by usual methods, but it's a bit technical. but it's by usual methods. You need to prove tightness, and you need to prove that any weak limit satisfies this equation, and you need to prove uniqueness of this equation in the proper space. But all these steps are sort of involved. Thank you. But it's not something that you should take the other patients to give the details. But it's kind of a method. And once we have this result, it is not difficult at all to see that the expected size of the cluster of in the line is bounded by a constant, universal constant, and to the 2/5. This one, how one proves, this is important that I at least say how one proves, because you make a simple estimate with branching and walk until you reach this value. And afterwards, you need to put in the attrition, so you kind of have a suitable Lyapunov function that controls, that doesn't go beyond. You know, it might change the constant, but you find something of this order. So the proof is a bit, this proof is not too hard, but one needs to settle the things in proper way. But once you have that, now it becomes something very simple. Once you have that, you know that if P vertex, so this, what I said was just something about how big is the cluster in one X. No, in one, there is nothing vertical, only horizontal. And it is of size, there is one individual, it is family, it is component, let us say, its component is of size expected value bounded uniformly by n to the 2/5 with a constant. That's what you know. And out of this, it's very simple by general comparison with branching process, that if you take a PV kappa times n to the minus 2/5, and kappa is small, then there is no possibility of percolation. But it's enough that kappa is less than, uniformly less than L, than 1 over L, say 1 over 2L, for instance, not 1 over L, half, something smaller. So it's the same as you do, no? You start here, this guy had a certain number of people in its component. Now from each of these, you can move, say, up and down, up or down, the 2 also has to do with that. And move up, say it was open, then it is bounded by, it can open all its cluster, and this is also n to the 2/5. And so on and so on. That's, you can immediately see in the same way that you prove that if you are on the plane and you have P as the probability for an edge to be open, no, if there is a P critical which is positive, because you make a trivial comparison with a branching process that ignores that the place is already occupied. So if you just look how many guys can you put in this component, this guy, if I do in this way, I can say, well, it's this branching, which is overlapping. It's bounded by these y's, where each of these are PV, and here it comes the guys which have this distribution, this size. So it's bounded by it's a subcritical branching process. That expected value is less than 1 because you took 1 over 2 less than 1 over 2L. So it's a trivial comparison. The same way, no, you have 4 neighbors and there is a P, and if now the P is less than 1 over 4, then it's bounded by a subcritical branching process. The same way that you prove on the plane. Here it's just that it's not nearest neighbor, but it's abstracted is just the same. So this is a simple thing. What's more involved is the other part. The other part is much more involved to prove, but you want to prove that there is a C2 uniform in the universal, for which if kappa is larger than C2, there is percolation. And the way we manage to do is to say, to do a suitable risk, what's called the one block renormalization, which you look at, you look at percolation structure, which has some dependence, is not totally independent, but this dependence is just nearest neighbor, say, just one dependent, just finite range. And but the probability to be open is very close to one. So you are going to replace some region of your space by something which you are going to call renormalized site. And you are going to say that this renormalized site is open if, well, I had some here, my stuff with a good density, this increased a bit with the times. And after a certain long time here, because this delta minus, I have something which is a little bit bigger. Say, this goes 4 minus 1, and this is 4. But after a certain number of steps. And if we can prove that this is such that there's this being good means there will be a connection. There will be a path of open sites in this within this structure. In order to prove that, that's where the difficulty comes in, is because well, you think, there is a diffusion, so if I start with a lot of guys, something grows a little bit because it's diffusion. So it grows. Okay. The point is that you need to find from one of these guys in the that you have at a certain level, you need to find an open vertex, an open edge going up, and this is so you need to localize things, and that requires that we had done the scaling limit with a given precision, which was n minus 1/5. And in order to make this, we needed something a little bit better. So we need to look at a scale a little bit more refined. So it's an analytical headache, but it's not so big trouble. So we can say that if in this more refined scale, a site is good if I have enough people there. And then we can prove that when this is good, then there is a good probability that I find someone connecting to the next floor. In fact, so that's to prove this, we just use nearest neighbor going up, oriented, because it's enough. And then, well, this is a little bit technical, but it is, I don't want to, because I am running out of time, so I don't want to say, but that's a little bit involved, that you need to look, but it's not, the other scale was good because that was the good scale for attrition, but one can deal with this a little bit. And also, in order to be sure that this thing will grow without depending too far away, we need to cut all the particles which are far away. We need to kill the process because we need to get something which is finite range. And then we use a result by Kessen of when it's to know that's one dependent, because this is important. And then the general result is that when you have this one dependent setup, then with probability very close to 1, you have percolation. And the way we are doing, we were saying for the site, and then we are going to declare that the bond is open if both sides renormalize, because you remember I was doing things with the renormalized site. And then in order to get the connection, we say that the renormalized edge, that means connecting two of those sides in this picture. Renormalized edge is good if this renormalized edge is good. If this vertex is renormalized site is good, then this one is good. And in this way, one managed to prove that for delta, you can have this very good probability. And then it's a general fact. Once you have finite range and the probability is very close to one, you have percolation by well-known facts. So I think I don't have time to speak about our motivation, but motivation came from an analogous problem for the easing with spread out interaction in one direction and localized in the other one. And we don't know the answer for that one. It is to be treated as percolation. It's a much more involved because it would be the FK percolation, which has a lot of dependence. These arguments don't go through. So I have no idea how to answer what happens for the easing. And so I don't want to go much over time. So these are kind of the references which we were using. So you see that somewhere there I went to write Lale and I wrote Lole. So I need to correct it. Okay, but these are the basic references which were used in doing this work. And I thank you very much. And I am at your attention for any questions. So.
Okay, then no questions. Let's thank everybody.
Okay. So let me take the opportunity that you are here because all this stuff with the easy model that I didn't enter, this was done. I mean, I think one of the driving forces of CATS models in the last several 3 decades, I think, is Enrico Presutti. And so he's behind many of those things of which I didn't have time to discuss, but it was not the purpose to discuss anyway. So I used that occasion to advertise that we have a series in the Brazilian Mathematical Society. And why Enrico Presutti? Because the last volume that we published, not only because for many reasons, but to say the last volume that we published is in honor of his 80th birthday, which was last year, and it's a collection of papers of many authors, and I want to say something about this just for 2 reasons. First, because it's a well-deserved honor that our mentor, and second, because this series is open access, and our goal is to have papers which allow, say, a graduate student to enter a new area, so kind of survey papers, long survey papers, lecture notes of advanced mini courses. So it's like, Springer Briefs is more, of course, everybody knows, and we are in the Brazilian Mathematical Society. But anyway, you take into consideration and you spread, and well, I leave this print copy, but it is in the web open. So thank you.